Hello. In the previous video, we have discussed the concept of phase space, and we have concluded that a phase space is an abstract mathematical space spanned by the coordinates as well as momenta of the particles of the system. It is used to visualize the dynamics of the system or the time evolution of the system in terms of the microstates of the system. And we concluded that for an n particle system free to move in three-dimensional space, the phase space will be 6n dimensional. Means it will consist of 3n position coordinates as well as 3n momentum coordinates. Now, in order to give you a physical concept, physical idea of how a phase space trajectory will look like, we will be discussing the simplest example from physical reality, which is the case of a one-dimensional harmonic oscillator. Okay. Now, hope you remember I told you in the introductory video that the phase space trajectory represents the time evolution of the representative point in the space. Now, since a phase space is not a reflection of the original physical space, you cannot expect that the phase space trajectory be looking like the physical trajectory of the system or the actual trajectory of the system. The actual trajectory may be linear, but the phase space trajectory may be curved, or maybe having some other shape, which we will illustrate by using this particular example. Now, let me consider as the topic, we have a one-dimensional harmonic oscillator, and there are several systems which executes harmonic simple harmonic oscillation, but we'll take the easier to imagine one, which is the case of a loaded spring. So here with me I have a spring of spring constant K connected to a mass M, and let this mass be moving on a smooth horizontal frictionless plane. So let me say that this be along x-axis, and the spring has been just tied firmly to the other end of the platform. So now this is our system. So let us say that the system is having some let me say that let this be its equilibrium position. So let this be the equilibrium position. So I can represent this one as x equal to 0. You are quite familiar about harmonic oscillators. Now let the spring be stretched by moving the mass to the right. So let me say that let this be the one of the extremes. So let me say that this is x equal to some plus a. We usually call it as the amplitude, right? And once you release it, you know that the mass will be just coming back due to the restoring force, and it will be compressing the spring to the other side. If it is purely simple harmonic, we know that our physical assumption is that the elongation and the compression will be by the same amount. So I can say this will be equal to minus a. So this much is equal to a to this side, and this is also a2. So what we call as amplitudes, plus a and minus a. And see, the system will be set into oscillation. Now, from the theory of SHM, simple harmonic oscillation, we have seen that the angular frequency of this system, is not the angular frequency of the system can be written or can be obtained as root of omega or omega square is equal to k by m, or omega equal to what? Root of k by m. That is the thing, right? Or what I can do, see the time period or frequency, all those things you can just understand. So this is the relation that we have obtained here. Now what I'm doing, I'm just considering the total energy of the system. I'm considering the total energy of this particular simple harmonic oscillator. This harmonic oscillator is having an interconversion of kinetic energy into potential energy and vice versa. So the total energy of this harmonic oscillator, total energy Okay, it's quite easy. You have done all this theory in your primers. We have developed all these things. So total energy, we represent it as by E. Capital E denotes the total energy. You know that it will be the sum of its kinetic energy and the potential energy. Kinetic energy I can write as either half mv square, or I can write in terms of its momenta. You know why I'm writing in terms of the momenta? How do you write kinetic energy in terms of the momenta? So it will be equal to simply the kinetic energy of the mass attached, because we neglect the mass of the spring. So it will be equal to p square by 2m. You know, this is the kinetic energy of a body having momentum p and mass m in terms of these quantities. It is nothing but half mv square itself. It is equal to p square by 2m. Okay, so plus what is the potential energy of a loaded spring? That is nothing but equal to, it is expressed in terms of its spring constant as half kx square, where x is the elongation or the compression, half kx square. Okay, since instantaneously this x can change, I'm not writing. At the extreme position it will be equal to half ka square, right, where it is purely potential, and kinetic energy will be 0 and all. We have discussed that, the graph what we have drawn and all. Okay, see, so this is the equation for the total energy, right? Now let me do one thing. Let me just rewrite this equation. That's better. As first term I'm retaining as such, p square divided by 2m, p square by 2m plus half kx square. So I'm going to substitute for k. So here this is simply omega square is equal to k by m, which will give you k will be equal to what? That is k is equal to simply m omega square. You are familiar with all these equations. Okay, so half, instead of k I'm substituting as half m omega square. Okay, and what is there? X square, right? So this is total energy E. On the left side you have got total energy E. Now let me do one modification. Just let me tell you, let me give you a hint what I'm trying to do. Our aim is to draw the phase space trajectory for this one-dimensional harmonic oscillator. And for a so it's a one-dimensional harmonic oscillator means what? Only one particle, because we have only single mass connected. So this is the simplest system that we have discussed before. One particle means having mass m and one dimensional. Is not the simplest case that we have discussed. Okay, and this is the only case that we can actually draw or represent in the physical space, because if it is two particle, then automatically the dimensionality will be getting increased to 4, right? If it is one particle, one dimension, the phase space is going to be two-dimensional. The phase space is going to be two-dimensional, because you need to represent only the one position coordinate x and its momentum coordinate px, right? One position coordinate x and its momentum coordinate what? Px. So if you want, you can just write this p here will be the px, because only one component is there. So let me make it more clear that this is px. Okay, so px square by 2m, only one momentum, it's along x direction. So I want to draw a graph or a diagram with one coordinate is x and other coordinate is px, right? Now for understanding its shape, the shape of the graph, I have to predict what will be the phase space trajectory. So in order to predict the phase space trajectory, I need to have an equation connecting x and px. I need to have an equation connecting x and px of the particular system. That is why when I wrote total energy, I didn't write in terms of half mv square. When I write in terms of half mv square, then I have velocity, but I need to have momentum. Momentum as one of the coordinate. I prefer momentum as one of the coordinate. Okay, that is why I have rewritten or re-expressed the kinetic energy in terms of momentum px. And here I need position coordinate. So here automatically when I write it half kx square, I have the position coordinate here, x is there. So now can't you see that this particular equation which I have written here is having both position coordinate and the momentum coordinate. Now it is easy. Now let me rearrange this expression in some way so that it gives you some standard equation. So let me do what to do. So now what I'm doing is, let me say that this is my equation number 1. Okay, so let me dividing throughout by E on both sides. Okay, what I'll get on one side, left side, it is equal to 1. So it becomes simply on the right side px square in the numerator divided by 2me. divided by 2me. So okay, plus the other one is what I'm getting is that it is let me rearrange this one, x square m omega square is there, I will use it, x square divided by 2 is there, no, right, 2 is there, so 2 is there, and I have divided by e, so that e also will be there, and there was an m omega square in the numerator, right, m omega square was in the numerator. So what I'm doing is that I'm putting that m omega square in the denominator. Now is it okay? Right, automatically this m omega square will come to the numerator there, so it's quite easy. So now you know why I have done like this. Okay, so this is my second equation. Now let us pause a little and think about this equation, right? So what is the form of this equation? Can you see that for a harmonic oscillator, here the mass m is a constant, mass of the object is or the mass here is constant, and also you have learned that in the case of a harmonic oscillator, in the case of SHM, the total energy is conserved, is not, even though the kinetic and potential energy is not conserved, the sum of kinetic plus potential energy is always conserved. We have just proved it also, because we obtained something like, E is equal to some total energy is half m omega square a square or capital A square, whatever it was. So that was our thing. So m is constant, omega is constant. Okay, for SHM, omega angular frequency is constant, and amplitude is also constant. There is no damping. If there is damping, that is damped one. So we imagine that there is no damping. There is no. That is why we have imagined that there is no friction here. Okay, so that it becomes a pure example of SHM, right? So the total energy is also a constant in the case of SHM, right? So omega is a constant for SHM. So these are the features of SHM that we have learned basically. So since all these are constant, you can see that whatever things are there in the denominator on the right side of the equation, all these are constants, right? So that gives you one benefit. What's the benefit? Suppose, now can you identify the sort of this equation? What is the sort of this equation? The sort of this equation is something like what is that? So it's just like x square by a square plus what, y square by b square is equal to 1, or 1 equal to whatever it is. Okay, so this is of the form, which is of the form, I can say, which is of the form, right, which is of the form x square by a square plus y square by b square equal to 1. Is it correct? Okay, if you want, you can just rewrite this one, the order. Okay, in place of x, I have x itself. Okay, so let me rewrite this one. So in place of x, you keep this x itself with position, and in place of y, means quantity along y axis, that is y, let me take px here. Okay, so just interchange the order of equation, it will be. So now in place of a square, you have got a 2e by m omega square, and in terms of b square, you have got what, 2me. So what I'm doing, I'm rewriting this equation for the sake of that. So it is, I'm writing as x square by root of, let me do it like this, root of 2e by m omega square whole square. Can I write like this? So it is x square by a square form plus what, px square by root of 2me, right, root of 2me the whole square, that is equal to 1. So that is the equation. Now you know this is a standard equation for an ellipse. Standard equation for an ellipse is not centered at the origin, ellipse. So what does it mean? It means that if you draw, it means that if you are drawing, sorry, just 1 minute, if you are drawing a graph, if you are drawing a graph with say, if you are drawing a graph with x and px as the axis, x and px as the axis. So what I'm doing, I'm taking here x, here I'm taking x, so x is taken here, and I'm taking px here, right? So both the position and momentum can become positive and negative. So this is the origin. This is the origin. What will be the graph looking like? So this equation says, equation number 2 or equation number, this is equation number 2 itself. Equation number 2 says, or 2a says that the graph between the two should be an ellipse. The graph should be an ellipse. Okay, so I can draw I am trying to draw the ellipse. So the shape may not be perfect, but you try to understand what I'm trying to tell you. Yeah. So the graph is going to be an ellipse centered at the origin. Okay. So let me put up an arrow here. So this arrow, this is what is known as the phase space trajectory of the one-dimensional oscillator. So our conclusion is that the phase space trajectory, this is our conclusion, phase space trajectory of a one-dimensional harmonic oscillator is an ellipse. That's a quite interesting result. It's a very standard result. Okay, and I told you in our previous discussion that how do we get a phase space trajectory? We have told you that a phase space trajectory is obtained by connecting the representative points of the system with the time evolution. Okay, or I can say that each point, that was another idea that we have discussed, each point in the phase space trajectory will be representing the accessible microstate of the system. So you take a point over here. This is a point on the phase space trajectory of the one-dimensional harmonic oscillator. So this point represents, okay, let me say point number 1. This is the representative point. Means it is an accessible microstate of this system. Or you take any point on the trajectory. All these points are representing the microstates, accessible microstate of this harmonic oscillator, this system, at various instants of time. And can't you see something? Some wonderful concepts are turning out. Can't you say that why this particular trajectory has been a closed curve? What's the reason? What's the meaning? I have put up an arrow which shows that the curve is there. You know, as the time passes, it means that as the time passes, the representative points will be actually getting repeated. Can you try to understand it like that? Okay. As the time passes, because it has got no beginning and no end, a closed curve has got no beginning and no end, right? So it means that for any periodic motion, that is actually another thing. It need not be always ellipse, but for a periodic motion, always the phase space trajectory will be a closed curve, because it should time and again pass through the same points. So for a periodic motion, you can always understand that, you can always conclude that the phase space trajectory will be a closed curve. That you can clearly understand. Okay. So now, before we end up this session, let me give you some more insights which may help you to understand the concept of phase space better, because this is one of the very few examples of phase space that you can draw actually. Okay. All these are, if it is 4-dimensional, you cannot draw like this. Only because it is one particle and 1-dimensional, you are able to draw in a 2-dimensional paper, right? Now I told you each point in this phase trajectory is representing the accessible microstate. So shall we try to identify some of the accessible microstates? For example, can you just tell me what does this point, what I am drawing just now here, point number 2, what does the point 2 denote? What does the point 2 denote? Now let's analyze the point 2. What is special about point 2? Point 2 is lying on the x-axis, means x coordinate is equal to 0, y coordinate is equal to 0. So I can say that this is something like, is not the maximum value of the x coordinate, that value that is being taken by the object, okay, because it does not go beyond this point. Means I can say this is nothing but representing the maximum value of the x. What's the maximum value of the x? As far as this particular motion is concerned, the maximum value of the x is plus a. So I can say this is actually plus a. This point is plus a. One coordinate is plus a. and momentum is, since it's a point on the x-axis, the momentum value should be equal to 0. So this is plus a0. This is plus a0. So automatically, you know what is, why this is minus. Okay, so this one is this particular point, this particular position. Okay, so this point is nothing but minus a comma 0 because its momentum is 0, because y-axis denotes momentum, right? So similarly, what is this point denoting? This point denoting, this point, you know, it's x equal to 0, so I can write 0 comma px. Px means what? Px is nothing but you know, what I can say, yeah, it should be, you know, this one. Okay, that is actually the semi-major axis and all, right? Okay, semi-major axis and semi-minor axis. So this one can be considered as a semi-minor axis. So automatically that will be equal to what? The value of p. So I can say that is root of 2me. That is root of 2me. Okay, that is root of 2me. And you will see that this a, okay, m omega square a square. How do you get that this is plus a? So you will see that from this relation, total energy relation, okay, you will get 2e by, you can understand that 2e by m omega square will be equal to a square. So a will be equal to root of 2e by m omega square, is it not? A will be equal to root of 2e by m omega square in terms of the total energy, and that thing is here. This is nothing but a. Not only this a, this here a denotes the amplitude here, right? So this one is root of 2me here plus 2me, and automatically this one is what? 0 comma minus root of 2me. Okay, the momentum value. So you can understand that this point number 2, I'm writing, this is point number 3, this is point number 4, and this is point number 5. Okay, so point number 2 here represents this particular state of the system. Point number 2 represents this particular state of the system. അപ്പോൾ ഈ ഒരു സ്റ്റേറ്റിൽ ഇതൊരവസ്ഥയാണ് അല്ലേ, ഈ സിസ്റ്റം കടന്നു പോകുന്ന, ഓസിലേഷൻ്റെ ഇടയ്ക്ക് കടന്നു പോകുന്ന അനവധിയായ സ്റ്റേറ്റുകളിൽ ഒരു പ്രത്യേക സ്റ്റേറ്റാണ് ഈ നമ്മൾ എക്സ് ഈക്വൽ പ്ലസ് 2. അപ്പോൾ ആ സ്റ്റേറ്റിനെ ദിസ് സ്റ്റേറ്റിനെ നമ്മൾ 2 എന്ന് പറഞ്ഞ ഈ ഫേസ് സ്പേസ് പോയിന്റ് കൊണ്ട് സൂചിപ്പിച്ചിരിക്കുന്നു. ഓക്കെ, ഇനി 3 എന്ന് പറയുന്ന ഫേസ് സ്പേസ് പോയിന്റ് എന്ന് പറഞ്ഞാൽ എന്താണ്? ഇതാണ് അല്ലേ, എന്ന് പറഞ്ഞാൽ എന്താണ്? ഇവിടെ നിന്ന് പിന്നെ അടുത്ത പോയിന്റിലേക്ക് പോകുന്നത്, ഇവിടെ എത്തിയ സാധനം തിരിച്ച് ഇങ്ങോട്ടേക്കാണ് പോവുക അല്ലേ, ഈ ലോങ് ആയിട്ട് ഇതിങ്ങോട്ടേക്ക് പോകും. അപ്പോൾ അത് അതിൻ്റെ മീൻ പൊസിഷനിൽ എത്തും. എക്സ് ഈക്വൽ ടു 0 വരണം. ഇവിടെ എക്സ് ഈക്വൽ ടു 0 എന്നാണ് വന്നിരിക്കുന്നത്. എക്സ് ഈക്വൽ ടു 0 ആകുമ്പോൾ അതിൻ്റെ മൊമെൻറ്റം എന്തായിരിക്കും നിങ്ങൾക്കറിയാം? മൊമെൻറ്റം മാക്സിമം ആവും, ബിക്കോസ് ഇറ്റ്സ് വെലോസിറ്റി ഈസ് മാക്സിമം അറ്റ് ദ മീൻ പൊസിഷൻ. ഓക്കെ, പക്ഷേ നിങ്ങൾ ഓർത്ത് നോക്കിയേ, ഈസ് നോട്ട് മൂവിങ് ടുവേർഡ്സ് ദ ലെഫ്റ്റ് സൈഡ്, ഈസ് നോട്ട് മൂവിങ് ടുവേർഡ്സ് മൈനസ് എക്സ് ആക്സിസ്. സോ വി വിൽ സേ ദ മൊമെൻറ്റം ഈസ് വാട്ട്? നെഗറ്റീവ്. അതുകൊണ്ടാണ് ഇത് നെഗറ്റീവ് ആക്സിലേക്ക് വന്നത്, മൈനസ് റൂട്ട് ഓഫ് 2me. Then it goes over here, and this point number 3 എന്ന് പറയുന്നത് എന്താ? അടുത്ത എക്സ്ട്രീമിലേക്ക് എത്തി, അതായത് it has reached this point. So this is 3. This is point number 5. Okay, it's not in order when I have written. And then you can see that ഞാൻ എന്തുകൊണ്ടാണ് ആരോ ഇങ്ങനെ ഇട്ടെന്ന് നിങ്ങൾക്ക് മനസ്സിലാവും. ഇവിടെ 3 എത്തിയതിന് ശേഷം അടുത്ത് എന്താ സംഭവിക്കുക? 3 എത്തിയതിന് ശേഷം ഇവിടെ എത്തുക. ഇവിടെ എത്തിയതിന് ശേഷം വീണ്ടും ഇത് തിരിച്ചിങ്ങോട്ടേക്ക് പോവുക. Okay, towards the mean position la poova. Towards the mean position poova ennu പറഞ്ഞാൽ it is moving towards what? Positive x direction. Positive x direction like move ചെയ്യുക എന്ന് പറഞ്ഞാൽ അതിൻ്റെ അർത്ഥം എന്താണ്? മൊമെൻറ്റം ഈസ് പോസിറ്റീവ് എന്ന് എടുക്കും അല്ലേ. ഓക്കെ, സോ മൊമെൻറ്റം പോസിറ്റീവ് ആണ്, അതുകൊണ്ടാണ് മൊമെൻറ്റത്തിൻ്റെ വാല്യൂ വീണ്ടും പ്ലസ് പി എക്സിൻ്റെ ഡയറക്ഷനിലേക്ക് പോയത്. അതിൻ്റെ വാല്യൂ എപ്പോഴും എന്തായാലും റൂട്ട് ഓഫ് 2me തന്നെയായിരിക്കും. ഓക്കെ, സോ ദാറ്റ് ഹസ് റീച്ച്ഡ് ഹിയർ. സോ ദിസ് ഈസ് പോയിന്റ് നമ്പർ 4. Okay, point number 5 and 4 just are representing the mean position, but the particle is moving, or the body is moving along opposite direction. Okay, so hope can you see that? What about the actual physical trajectory of the system? One dimension harmonic oscillator ആയതുകൊണ്ട് ഈ ഒബ്ജക്റ്റിൻ്റെ ആക്ച്വൽ ഫിസിക്കൽ ട്രാജക്ടറി എന്ന് പറയുന്നത് എങ്ങനെയാണ്? ഈസ് നോട്ട് ജസ്റ്റ് മൂവിങ് അലോങ് സ്ട്രെയിറ്റ് ലൈൻ അല്ലേ, അങ്ങോട്ടും ഇങ്ങോട്ടേക്ക് ഇങ്ങനെ സ്ട്രെയിറ്റ് ലൈനിൽ അങ്ങോട്ടും ഇങ്ങോട്ടും പോയിക്കൊണ്ടിരിക്കുകയാണ് ചെയ്യുന്നത്. സോ ദ ആക്ച്വൽ ഫിസിക്കൽ ട്രാജക്ടറി ഈസ് എ സ്ട്രെയിറ്റ് ലൈൻ. But what about the phase space trajectory? The phase space trajectory is not straight line. Instead, it becomes what? An ellipse. This is why I told you that the phase space trajectory of a dynamical system need not be a reflection of its physical trajectory, but it encompasses, or it has in its shape and in its features a lot of information. അപ്പോൾ ഈ സിസ്റ്റത്തെ പറ്റിയുള്ള നിങ്ങൾ ഓർത്ത് നോക്കണേ, നമ്മുടെ ഈ ഹാർമോണിക് ഓസിലേറ്റർ എന്ന് പറയുന്ന ഈ ഫിസിക്കൽ സിസ്റ്റത്തെ പറ്റിയുള്ള ഇൻഫർമേഷൻ മുഴുവനായിട്ട് കോഡഡ് ആയ രീതിയിൽ, ഒളിഞ്ഞിരിക്കുന്ന രീതിയിൽ ഈ ഒരു സിമ്പിൾ ഡയഗ്രാമിൽ അടങ്ങിയിരിക്കുന്നു എന്നുള്ളതാണ് ഇതിൻ്റെ ബ്യൂട്ടി. ഓക്കെ, that is why we say that the entire information regarding, it's not microscopic information regarding the dynamical system is actually hidden in, or it can be represented by a simple plot, what you call as what, phase space, which is spanned by the coordinate and momenta of each of the particles which constitute the system. Okay, so that's about the phase space trajectory of a one-dimensional harmonic oscillator. So see that you read or see, just try to understand the concept better. So these are one of the limited examples that we can clearly discuss, and you'll be able to imagine. If you extend your imagination, certainly you'll be able to do this one for large particle systems, which we will do by a concept what is known as, I had introduced that one, a concept what is known as ensemble concept. Ensembles, and ensembles are nothing but a collection of such representative points, all possible representative points that we will just discuss in your postgraduate classes, because it's not directly mentioned in your syllabus. Okay, anyway, that's all about it. Thank you.